Hey everybody, Mr. Judson here. So let's see, last week we were working on verifying trig identities, which the word identity just means something that's true. So this is something that is true. Let's prove or verify that it's true. And you know, you might ask yourself, why are we doing this? Well, I just got done preparing for the calculus class. And we're doing this very thing. You know, we're doing more than this. We're doing something called integrals, which we don't know what that means yet. But they're having to take trigonometric expressions and change them to something else in order to do the work that they have to do. And so a lot of times we may not have a good real-world example why we have to do this, but we do have good mathematical examples in order to push forward and understand, you know, stuff at the next level. We got to know some previous information. You know, it's kind of like, when am I ever going to add or subtract fractions in real life? You know, well, here we are. We're using this later on in a higher level math class where we have to get common denominators and add things together. So that would be why. So to verify this, I guess I would look at this problem first and say, okay, which side's more complicated? They both look pretty complicated. But on this side, I have two terms. Okay, remember, plus or minus sign is what separates terms. Over here I just have one fraction, which is considered one single term. To me that says this is the more complicated side. I only see sines and cosines here, so I'm probably going to want to change this to sines and cosines. I'm probably also going to want to get a common denominator and add these together. So you guys go ahead and try this one. All right, so probably the question is, do I get a common denominator first and add these together? Or do I change the sines and cosines first, simplify this, and then get a common denominator add together? I don't know if there's a good answer to that. I think you just have to pick one and try. I think I'll just go ahead and get a common denominator and add these. So I'm going to multiply the bottom here by 1 minus tangent x. And then I'll do the same thing to the top, 1 minus tangent x. So if you did this different, don't change what you've done. Let's just see if we end up with the same information at the end. Okay? All right, so if I distribute this, I would get a cosine of x minus a cosine x times a tangent of x minus this cosine of x all over the common denominator, which is 1 minus tangent of x. So right away I see that cosine x minus a cosine x, that adds up to 0. Now I think I'll take what's left and change to sines and cosines. So in the numerator I've got a negative cosine of x times sine x over cosine x. And I'm dividing that whole thing by 1 minus sine x over cosine x. So, again, I see that I can cancel some cosines here. Cosine x divided by a cosine x is just 1. And so now what I have is a negative sine of x over 1 minus sine x over cosine x. So again, this is a spot where you can get a common denominator and add these two things together, and then, because we're dividing by that fraction, flip it over and multiply. You can do that. That'll work. But I always say that when you have a complex fraction, which means a fraction within the fraction, multiply everything by that least common denominator. What that does is it does the same thing, but it just does it in one step instead of maybe 2 or 3. So the only denominator here is a cosine of x. So I'm going to multiply every term by cosine x. I'll do it there, I'll do it here, and I'll do it here. And so these cosines will cancel. And so now what I have is a negative sine of x cosine of x. Remember what I said last week, always look up here and see what you're working towards. Make sure that what we're doing is making sense. And so far it's making sense. I see that negative sign. I'm going to have to do something there, but I see that I'm moving closer towards this. Here I have a cosine of x minus a sine of x. So the only thing I see is that my denominator is switched around. Here the cosine's negative, here it's positive. Here the sine is positive, but here it's negative. So to me that says let's just move this negative sign down into the denominator, and then I'll distribute that to each of these, and that would give me what I want. So I now have sine of x times cosine x. When I distribute this, the cosine will be negative, the sine will be positive. So I'll write it this way, sine of x minus cosine of x, and that's what I was looking for. So you can tell these are getting a little bit longer, a little more complicated, and that's okay. We just need to think our way through it and take as many steps as you need. All right, so here's another one to try. And right away I'm noticing something that hasn't happened before. I don't have the same angles here. You know, here I've got x, here I've got y. So if I want to change this to 1 over a tangent y, I can't cancel those because the angles aren't the same. You know, to be able to cancel things, everything has to be identical. So now I have to decide which side is more complicated. I just got done telling you guys, you know, if you have two terms here and you want to be able to add those and get a single term over here, that's the more complicated side. But I don't know if I really believe that on this one. To me, this looks more complicated. I think I want to work with this side. That's just the gut feeling that I get, and try and make this look like that. I'm also not sure if I would change the sines and cosines, and the reason I say that is because the trig function I see here is the same as what I see on this side. So I might be more inclined to just work with tangents and cotangents, but that doesn't mean it would be wrong to change the sines and cosines and then eventually at some point change back. You know, you have to kind of decide that on your own. You guys go ahead and give this one a shot. All right, so even though I say this is the more complicated side, if this was a test question and somebody chose to work with this side, I want to make sure everybody understands that's not wrong. We could logically go through and somehow get back to this right here, and I think that would be fine. There's nothing wrong with it. So if you looked at this and saw something and chose to work with this side, that's okay. Remember, there's always more than one way to do these problems. So I think what I'm going to do is I'm going to go ahead and divide this up into two terms just because I see two terms over here. I've got a tangent of x over tangent x cotangent y plus cotangent y over tangent x cotangent y. You know, normally when I do these, I try to think, you know, if I want to divide this up into two terms, I'm also trying to think about what the next step would look like. I don't think I really thought about that this time, but had I thought that, I would have realized this is a good way to go because I'm going to be able to cancel some things here, right? So being able to think a step ahead is a good thing. All right, so these tangents cancel, and I'm left with 1 in the numerator. These cotangents cancel, and I'm also left with 1. So now what I have is 1 over a cotangent y plus 1 over a tangent of x. And 1 over a cotangent is equal to a tangent. If we go back and look at our basic identities, this is our tangent and cotangent reciprocal identities, right? A tangent equals 1 over a cotangent, and a cotangent equals 1 over a tangent. So I could just call this tangent y plus cotangent x, and there it is. That's what I was looking for. All right, so I've got the square root of 1 minus a cosine theta over 1 plus cosine theta, and that's equal to 1 minus cosine theta over an absolute value sine theta. That absolute value signs, those kind of make people go, oh gosh, this is going to be a hard one. We'll worry about that in a minute here. One thing that I see is this numerator is the same as this numerator. And I feel like the only way that can happen is if I was to get another 1 minus cosine theta. So I had two of those up here that are being multiplied, and then I take the square root of that and I get just 1. Okay? If this was squared, the square root of something squared is just that right there. That's something that catches my eye. And one of our strategies that we've talked about is multiplying top and bottom by a conjugate. And so I think that's where I would go with this, is I would take the conjugate of this denominator, 1 minus cosine theta. What you do to the bottom, you got to do the same thing to the top, 1 minus cosine theta. And I would then kind of push forward with that. You guys go ahead and try it. All right, so if I do that, I've got 1 minus cosine theta squared. I'm not going to multiply that out because I want to be able to take the square root of something squared. That's what's going to give me this right here. In the denominator, though, I think here I do want to multiply this out. And what I'm going to get is 1, and then I get a negative cosine theta, and then plus cosine theta. So those middle terms will add up to 0, and then minus cosine squared theta. So the reason we multiplied by the conjugate was it creates something that looks like part of a Pythagorean identity. And so, if I go back and think to myself, all right, sine squared plus cosine squared equals 1. Well, 1 minus a cosine squared, if I move that over here, move that cosine over here, it becomes negative. 1 minus a cosine squared is just equal to a sine squared. And so again, if I'm going to take a square root of something squared, I need to see a sine squared here. So now what I have is this. Square root of 1 minus cosine theta, that whole thing squared, over sine squared theta. And so the square root of this is just 1 minus the cosine theta. Square root of a sine squared is going to be just a sine theta. And so our only question now is, why do they have those absolute value signs in there? Well, the reason for it is when you take the square root of something, you always get a positive answer. Okay? If I say this to you guys, the square root of 4 equals 2, we'd all go, well, yeah, of course it does. But it's not plus or minus 2, right? The only time that happens is when you're solving an equation and you use the square root as a way to solve. There are two possible numbers I could plug into here and get 4 for an answer, either a positive 2 or a negative 2, right? But if I'm just doing the square root of 4, the answer is positive. Well, I know that a sign can be negative, but I'm taking a square root and I'm supposed to get a positive answer, and so that's why they put those absolute value signs there. So the next question is, well, why didn't they put them in the numerator? Well, the largest value you can get for a cosine is 1, right? Remember our unit circle? Cosine is the x-coordinate. The farthest I can get away from the origin is 1 unit, so 1 minus 1 is 0. This will never be negative right here. If the cosine happens to equal a negative number, let's say it equals negative 1, then I'm going to do 1 minus a negative, which means add, so I can get as high as 2. But when I subtract numbers, I can't subtract more than 1. So this will never be a negative value. Okay, it will always be positive. So they just left them off. If somebody would have done this, let's say the direction said to simplify, and you did this, I'd go, perfect. I'd be happy with that. Yeah, this will only be positive, but this could be negative, so we're saying make sure the overall fraction is positive. Okay? So absolute values seem like such an easy idea because in reality they just mean how far are you from zero? It's a positive distance. It seems so easy. But every time you put them into something else, like this, all of a sudden it becomes a little confusing. Okay? All right, so we got what we were looking for. There it is. All right, you guys go ahead and give this one a shot. So it seems pretty obvious this is probably the more complicated side, since the only thing I have here is cosine to the fifth of beta. If that's all I'm going to have at the end is cosines, to me that says I need to try and change everything over here to cosines. And the only way I'm going to be able to do that with a sine is through those Pythagorean identities. So I think my first step here is I probably want to try and factor this. So this would be sine squared beta times sine squared beta. This could only be 1 times 1. And if I make both of those negative, when I FOIL this, I would get a negative sine squared and another negative sine squared. That would be 2 of those. And negative times negative is positive. So that does work. And now it looks like a Pythagorean identity. So sine squared plus cosine squared equals 1. I want to have a sine squared minus 1. So I'm going to bring the 1 over to the left side here. Sine squared minus 1. When I move that cosine back over, it becomes negative. So what I'm saying is sine squared beta minus 1 is equal to a negative cosine squared beta. So let's put that in here. I've got a negative cosine squared beta times another negative cosine squared beta times a cosine beta, and you guys probably see it now. Negative times a negative is positive. Add the exponents, you get 2 plus 2 plus 1. That's cosine to the fifth of beta. And there it is. So that one looked kind of messy, but really that was probably the easiest one we did today. Alright, so that's it. That's what we have for today. So this would be assignment number C10, page 387. We're going to do 23 to 37 odd. And just kind of looking a step forward, what we have for on Thursday this week is solving trig equations. And all this stuff that we did with simplifying and verifying, it'll help us out with that as well. All right, so that's it. You guys have a good day. Stay safe. I'll see you on Thursday. Bye.